From the 2005 AP Calculus AB exam, the free response question 1, let f and g be the functions given by f of x is equal to 1/4 plus sine of pi x, and g of x is equal to 4 to the negative x. Let R be the shaded region in the first quadrant enclosed by the y-axis and the graphs of f and g, and let S be the shaded region in the first quadrant enclosed by the graphs of f and g as shown in the figure above. So we have the region R and the region S. A, find the area of R, B, find the area of S, and C, find the volume of the solid generated when S is revolved about the horizontal line y equals -1. We'll start with part A, find the area of the region R. Naturally, because we're finding area, we know to use an integral, because an integral will yield the area under a curve. And that's what we're trying to do. We're trying to find the area between the curves f and g. Additionally, we know that with an integral, we have bounds. Looking at the region R, we can see that it's probably easiest if we integrate with respect to x, that is, dx. Because if we were integrating with respect to y, we would have to cut the graph into two, because we would be looking at the area between this curve and the y-axis, and then this curve and the y-axis. However, integrating with respect to x, all we have to do is find the area between this curve and this curve between two defined boundaries. Okay, so part A, what do we have to do first? We have to find this upper bound. We know the lower bound is 0. We want to find the point where f and g intersect. Well, we know that f is 1/4 plus sine of pi x, and g is 4 to the negative x. Setting these equal, we'll be able to solve for x, which is what we want. We want to know the x value at which the two functions intersect. That will give us our right or upper boundary for this integral. Now, in terms of the AP exam, we don't have time nor the means to solve this type of equation. So what we'll do is plug the two functions f and g into our graphing calculator and solve for the intersection point. When we do this, we get x is equal to 0.178218. It's important not to round here, and so it's best if you store this value as some variable, maybe a. So store it as a, then when you integrate, you want to integrate from 0 to a, where a is equal to 0.178218. What's also nice is that if you state this as a given in your exam, if you state a is equal to this, when you write your integrals, you can say 0 to a, as long as you connect that a is this value. And so, further along in the problem, maybe in another part, as long as you've stated what a is equal to, you don't have to keep writing such a long number, you can just write a. So that saves a lot of time and can prevent a lot of error, especially when you store the limit as a. All you have to do is type in a instead of typing in this whole string of numbers where you might make a mistake. Anyway, so the integral from 0 to a of what? We want the area under the curve. But really here we have the area between two curves. We have the area that is under g but over f. As such, we want g of x minus f of x dx, which is the integral from 0 to a of 4 to the negative x minus 1/4 minus sine of pi x dx. Using our calculator, we find a value 0.065. We'll want to round to at least a few decimal places. Now, when the scorers look at your problem, they're going to be looking for three main things. They want the limits. So do you have 0 to a, or 0 to 0.178218? Those are important. Without the correct limits, you will miss one of the 3 points for part A. They also look at the integrand, so g of x minus f of x. Make sure that you subtract the lower function from the upper function. If you're confused at all, think about if this entire region was R, what would you do then? You would just have the integral from 0 to a of the upper function g of x. Well, really, that's g of x minus a lower function, which is just y equals 0. So g of x minus 0. But instead of going all the way down to 0, we're going down to f of x. So it's g of x minus f of x. Just a little clarification. And what's really important is to include the dx. The integrand is not correct without dx, or if you mix it up with dy. A good way to make sure you know if it's dx or dy is to pretend like you're slicing. So you have to slice from your bound to your next bound in small rectangles. Whatever axis you're slicing through is the axis to which the integral is in respect. As such, we are slicing the x-axis, we have dx. And finally, 1 point for the answer. So part A is worth 3 points. Part B, we want to find the area of S. This is very similar to part A. We have to subtract the lower function from the upper function, although now they've switched roles after this intersection point. But again, we want to use an integral. We know the lower bound is a, as we solved for, and it's the intersection of f and g. Now we have a second intersection point, which will be our upper limit. Again, using the data that is already in your calculator, you can solve for this second intersection point by tracing or finding an intersection point. But when you solve for this intersection point, you'll find that it's x equals 1. So you have the integral from a to 1, so from here to here, of, now f of x is the top function, so f of x minus g of x, again slicing in the x direction, so dx with respect to x. We don't want to integrate with respect to y, because here we would be integrating from the same function to itself, and that can't happen. This would be from f to f. As such, we integrate with respect to x so that we have f to g in all places in area S. So for B, again, area is from a to 1 of f of x, which is 1/4 plus sine of pi x, minus g of x, which is 4 to the negative x, dx. Utilizing our graphing calculator, we find that we get a value of 0.410. Scoring goes along the same lines as part A, bounds or limits, the integrand including the correct dx or dy, and finally the answer. So with A and B combined, we're at a total of 6 points. For C, we want to find the volume of the solid generated when S is revolved about the horizontal line y equals -1. So if we draw this line at y equals -1, we know that S is revolved around at y equals -1, like so. And so what's the best method in which we can calculate this volume? There are a number of methods possible, like shell, washer, disk, and we'll analyze all three to see which one would be most appropriate. So if we look at disk, that's not going to work because we have this shape, then we have some axis about which we're rotating, and so then we'll have this shape on the other side. So we'll have this whole gap of a varying radius within the middle where there's nothing, and this donut-like shape that goes all the way around with nothing on the inside. So a disk doesn't make sense because there's this space in the middle. Washers, this makes more sense because we have a middle part that's empty, and then an outer part in which the volume is contained. So like a washer, this shape is similar. The third possible method is shells, in which we would use cylinders of expanding size in order to calculate the volume. In this case, we would be integrating with respect to y, because our cylinders would expand this way, but like we were talking about in part B and part A, this is not a great way to do it, because we would touch f on both sides, and we can't integrate from f to f. We have to integrate with respect to two different functions, or else we can't do anything. So our best option will be washers, because we can still integrate with respect to x, and we'll always have unique upper and lower functions, f and g, from which we can integrate. So the formula for integration with washers is the integral of pi, the larger radius squared, minus pi times the smaller radius squared, in this case dx. The big radius will be this outer part here, because that will be the absolute maximum radius that we achieve with this donut-like shape. Little r will be this inner function, and it is the minimum that the minimum distance from the axis to the donut shape, or we can think of it as the maximum that the empty space contains between the two volume parts of the donut. So we can pull out pi because it is in both terms. Then we have the integral. What are we integrating from? Since we're revolving S, we can use the same bounds that we used in B when we found the area of S. So we integrate from A to 1 of big R squared. What is big R? Big R is f of x. So we have f of x, but not only that, we have this axis about which we're revolving that is an additional unit of 1. As such, we have to increase f by 1 before we square. Had we revolved it around the x-axis, then f of x would be sufficient. However, we have this extra distance, making big R f of x plus 1. It is this distance given by f of x at any point, but we have to add the addition of 1, and then square, as we see here. Then we subtract little r squared, and little r is g of x plus 1 quantity squared. This whole integrand with respect to x, so dx. Now, I'm running out of room, but plugging this into your calculator will yield a value 4.558. Now, when the College Board is looking at your paper, they're going to be looking for several key things. To get 2 points, 2 out of the 3 points for this part C, is dependent on this integrand, what is contained within the integral. So you have to have the requisite components that make up the solution to find the volume. So pi r squared minus pi little r squared, if you're using washers, which is the best way in this case. But if you're using shell method, the integrand will be different, but it better be accurate because that is a substantial chunk of this part's points. Then for 1 point, you have to get 3 things correct. The limits of integration, this constant here, otherwise your answer is wrong, and then the answer itself. If any one of these 3 parts is incorrect, you lose that point. So the most important part is setting up this integral. If there's no time to solve for the answer, that's okay, as long as you get this integral set up, because that's the part that really shows your knowledge of this problem and is 2/3 of the points of part C. So hopefully this video helped you solve the AP Calculus problem number 1 of the free response section from the 2005 exam.